but let me do attendance. Takes a little bit of time. Braden. Braden. Cole.
Here.
Cole. And then Xander Barr. Probably, I forgot to check, probably removed. Samantha. Olivia. Philip.
Yo.
Jeff.
Here.
Sander.
Here.
Josiah.
Here.
Drew.
Here.
Drew. Junior.
Here.
Diana. Is it Diana or Deanna?
Diana.
Diana. John. Chris. Maddie. Where's Maddie? Nathan? No, Nathan?
What's his last name?
Smith? Yeah, Nathan Smith. Was here yesterday. Oh, you know what? I think he moved to the other section. Oh, that's right. Clayton? Clayton. Okay, and then nobody added? Is everybody? Okay, perfect. Perfect. Okay. Yes. All right. So first of all, I guess Alex, the link should be working now. Can anybody confirm that? Anybody try that?
Yep.
Yes. Okay. Good. Yeah. I realized it was my fault. I realized what was going on. So I can do like student view. Like I can go to Blackboard and student view and see like a student sees it. But then when I clicked on the link, it still put me in the instructor thing. So when I clicked it, it said like choose your stuff. I thought that was working for the student side, but that was actually the instructor side. I had to choose the class. I haven't done this class since like last summer. So you forget some of those small things, but so yeah, I forgot to actually link. I forgot to link them to the course to Alex, but that's why. But the Alex course was set up and the Blackboard was set up. I just didn't link them anyway. So whether the grades, whether you can go through that link and log in or not, it's okay either way. As long as you can get into Alex and do your work, that's what really matters. Like I said, the worst case scenario is just I have to import the grades manually, so it's just a little slower. So it's not a big deal. If you already did that, that's fine. That being said, I only see 13 of us. There should be 16. So 3 of you are missing. So if you're having trouble with it, let me know. And more or less, like I said, today I figure I'll probably just go through my normal like day one kind of content talk. But after today, after you guys have had some time to work in Alex, done some homework, done some modules, everyone's kind of worked on it, this thing will start to fill out. There's like this class, there's like a class pie chart. And I can look at like the classes, like what's to be learned, what's to be done, things like that. And then I can start to tailor the instruction to this individual class. Okay, so that's the general plan. Maple's not for you guys. I need this one. All right, and we are 9 a.m. All right, so I guess before I get started, is anybody that didn't get the syllabus or had any questions on anything initially? Feeling okay so far? Not too overwhelmed, hopefully, by all the syllabus, all the information thrown at you yesterday. Not just from this class, from all classes. All right. So the general idea here also, of course, if you do have when you have questions before class when something comes up, usually I do it here in like student questions. Here I just wrote this little blurb about Alex, and then that's for I haven't done that yet. That's when I reserve a room. That's the room I'd like to reserve. I'll just leave that there just in case. And then once we have quizzes, if we have questions on quizzes, I usually put them here. Like I said, with quizzes, I always post a blank version and the solutions to Blackboard after we've taken it, of course. But if we have questions on it, I'll put it here. So other than that, we'll just take a look at section 1.1 and kind of go through some of the preliminary information. And then, like I said, we can start to look specifically at what we need from Alex. All right, so the first thing I want to talk about is just sets in general. So what is a set? So a set is just a collection of objects. So a set I mean, you all know that. That's pretty obvious. Like, I mean, we could be a set, right? We're a set of students and a faculty member, I suppose. But you could have like this class, the students in this class and the students in the other pre-calc. So those are sets. Obviously, mathematically, we're usually interested in sets of numbers. So we have to have ways of representing sets of numbers and write down and be able to read it. Math is a language that is very much fundamental to everything you're doing here. basically we have something in the world around us and we want to represent it on paper and we want to communicate it with each other. That's what math is. Math is the language that lets us do that. So how do we write a set? The notation we use for a set in general is a squiggly thing called a brace. It's on your keyboard. That's what it looks like. It's usually above enter, above the square brackets. So that's called a brace. Let me actually write that down even. Just the name. Because these aren't going to go in. They're grouping symbols, so they go together. These are braces. And then you have your, these are usually just called brackets or square brackets, or I've even heard them called like square parentheses, but I think that might be other countries. But usually I refer to these as brackets. And then, of course, you have your parentheses, your rounded parentheses. Actually, I guess plural would be, anyway. So those are just symbols, right, that have existed before math. They're just symbols, but we use them in math for certain reasons. So when you see this, you read this as the set. And then we can put objects in here. So let's just say, like 1, 2, 3, 4, 5. And then I close it. So this is the set of numbers, right, 1 through 5. Okay, 1 through 5. And then we could also, often what we do is instead of referring or writing that whole set all the time, we'll give it some sort of letter. We'll give it a letter like, let's say S. It doesn't really matter. I'm just going to use S. So we can say S is, so we can say S, and then this would be like is, right? So you can see what I mean. Math is a language. The whole thing, you can read this as a sentence. It says S is the set 1, 2, 3, 4, 5, right? Likewise, we could have, say, T. And let's say T is the set 5, 6, 7. Okay. So those are just sets. They can be sets of objects. Notice the braces are used when I want a finite set. So that's very important that these are finite. So we are not getting into the idea of like countably infinite and uncountably infinite and stuff. So finite, you can basically think like, well, look, I can just list them all out. I can count them all out. So basically, if you can list out all the elements, that's what finite means. Obviously, really anything in reality is finite as far as we know. I mean, space can't go on forever, but we don't know how far it goes. But or maybe it does go on forever. I don't know. But that's as close to infinite as we get. But anything on our world is finite. Resources, people, and so on. But we often deal with infinity, of course, mathematically as the sort of theoretical limiting value of something. But we'll get to all that stuff too later. All right, so these are finite sets. And so then what can we do with these sets? So then we have set operators. And you already know operators. You know operators are called like addition. The plus sign is an operator. The subtraction sign is an operator. The division sign is an operator. The multiplication sign is an operator. Well, set operators, we have our union and intersection. So we can say something like S union T. That's it's not a U. It looks like a U, but it's not a U. Maybe make it a little smaller so it doesn't look like a U. And so you read this as union. And so you can see I can write S and T. It just looks a little cleaner, but actually means the exact same thing as, and you don't have to write this one if you don't want to. It's a lot of writing. That's why we don't do it. But it's the same thing as saying I want this set, and I want to union it with this set. And so what I want to talk about today is, well, what does that actually mean? Or one of the things I want to talk about is what does union mean? So union means you take everything from one set, everything from the other set, and you put them together. So you get a bigger set that contains everything from each one. So we're going to get the set 1, 2, 3, 4, 5, 6, 7. That's a 7. So if we took the set of students in this class and the set of students in my other pre-calc class, or sorry, people, not students. Let's say the set of people in this class and the set of people in my other pre-calc class, you would have all of you, all of my other students, and myself. But I wouldn't magically double, right? So if you're in both, if there's an element, and then these are called elements. I should mention that too as well. Sorry. Each one is called an element. Okay, each individual piece. So if an element is in each set, it's not going to magically double. So you don't write it twice, you just write it once. So like on myself, like I said, if we took all the people in this pre-calc class, all the people in the other pre-calc class, put them together, I would just be in that set, right? I'd be in that set, but I wouldn't double. Okay. So then that's kind of like addition. You can basically think of that as set addition. That's really kind of what's going on there. You're taking one group and the other one, putting them together. So then the other operator that we often use is called intersection. And it's an upside down, same symbol, but upside down. It's not an N. Don't give it like, it's important I say it's not a U. Don't give it like a tail. It's not a U. Don't give it like a little flag thing like an N. It's more of a parabola shape. It is this U shape, but no extra pieces to it. All right, and so that would be, I'm not going to write out this one. Let's just write out the actual set. So that is the elements that are common to each set. So is there anything that's in both of the sets? So what is the intersection between S and T? 5. So we'd have a set with a single element, 5. Likewise, if we took the intersection of this pre-calc class and the other pre-calc class, I would be the only common person in those two classes. Well, unless you guys want to double take the class for some reason. I'd be the only one that's in both. Okay, good. All right, let me quickly introduce another set so we can do a few other things. So let's say R is the set, let's just say 6, 7, 8. And let me zoom out a bit so you can see all 3 sets. Okay, and let's have you tell me what, let's do T intersect R and S intersect R. So notice the intersections, you just get a new set. So this is a new set, right? And if we can actually write it out, we'd like to, but S intersect R is just another set. Okay.
I got a question.
Yeah.
N still stands for union, right?
No, intersection, sorry.
Intersection.
Well, I could put it here. And it's not, like I said, it's not an N. Yeah. Sorry, I didn't mean to do that. Thank you. Intersection. Okay, so what do we think? What's the intersection between T and R? 6 and 7. Good. So the intersection between T and R would be the set of 2 objects, those 2 objects. And then what's the intersection between S and R? Nothing. So we actually write empty braces like this, and you would call that the empty set. Literally the set containing nothing. It's essentially like the set equivalent of 0, if you think about the number 0, of course. But it's not, you don't put a 0 in there because 0 is an element, right? If it had the element 0, that would be something else. This is literally a set with nothing in it. And then we do have a notation for it, and unfortunately it looks a lot like 0, but it's not 0. There is a symbol. You don't really have to worry about this in this class. I just want you to know it exists. It's basically like a more dramatic 0, kind of like that. It's a symbolic notation for the empty set. I don't think I have it typed in. Actually, maybe I do. I might have it typeset. Yeah, there it is. So there's typeset in the notes. You can see what I'm trying to draw. We'll get to those rounded E's in a second. So that's what we're writing. So this, like I said, it's not a U, and it doesn't even look like the letter U, right? And when it's typeset, and it's not an N, it doesn't look like the letter N, but that's the symbol we're looking for. And then this is the empty set. Usually, if people do put a bar in 0 when they write the number 0, I never do, but if they do that, it looks like this, right? If you see 0 like in money or things like that. So it's the bar goes outside of the 0 anyway. All right, so we just did this example. I just made them up differently. Okay, so one other important notation that you're going to see all the time in your mathematics dealing with sets is element of. So this, like 5 is an element, and how do we show that? We say something like 5, and then we put this sort of rounded E, and I'll show it to you again, typeset over here. So this guy right here. So it kind of looks like a rounded capital E, but it's not. Again, it's just what it looks like. I'm just trying to help you draw it. So we have 5 is an element of S, and then we have 5 is not an element. So if you think about equal to and not equal to, right, you just cross it off. You have like the forward slash. So we have the same sort of thing. You put not an element of R. Right, so they're just talking about whether it's in there or not. So the way you would read this is element of. You can think of it informally. We're talking about element of the set, or you just say in, right? Well, we were saying if it's in the set or not, right? Question?
What if it was an element of S and T?
Then it'd be in their union, right? So I mean that's fine. We can say where's T? Where did I make T? Yeah, that's fine. We can also say 5 is an element of T. We can also say 5 is an element of S union T. We can also say 5 is an element of S intersect T. You understand the union and the intersection? Whoops. The union and the intersection are just new sets, right? Yeah, there's nothing there. There's nothing exclusive about it. It's just a way we indicate if something's in a set or not. Okay. Any questions on this preliminary information? Is that too fast, too slow? Okay. Feeling okay? Okay. Okay. All right. So now, why did I mention the bracket and the parentheses? So this is finite. So of course, if you have questions here, please ask, because this is easier. It's easier when it's finite because you can see everything. I mean, finite might be tens of thousands of digits, but if you can still see them all, technically you can match them all, and it would be easier. Infinite becomes a lot harder. So how do we show that we want an infinite set? That's where we use our brackets and our parentheses. So how do I want to do this? I have interval notation, set notation. Let's just do it down here. Let's just do this. So what is the set? We don't have to call it anything. I'm not going to call it S, T, or R anymore. We'll just say, what does this mean? So if we have parentheses 1, 5. Okay. So over here in gray, let me put brace 1, 5. This set has how many elements? 2. Notice, very easily counted. This set, has infinitely many. Elements. Actually, let me even make it, oh yeah, I made it 5. Yeah, 1 and 5, 1 and 5. So we call this one, this is infinite. Sorry. Infinite. So let me represent this on the number line. So the number line represents all possible real numbers, right? If it's a real number, if you plot it on the real number line, that's what that is. We just draw a line, but that's what that's representing. So of course you can put 0 if you want. You can put 1, right? You can put 2. You can put let's put I guess I'll put 3, 4. Let's put pi on there. Let's put e on there. If you don't know what e is, it's okay. It's a number. 2.72 approximately. Pi is 3.14. I'm just putting weird numbers on there. Let's see, square root of 2. Square root of 2 would be 1, whatever. I'm just putting odd numbers on there. Okay, so number line. So we have all these numbers, and then you go to 5, you go to 6, and you go to negatives, right? -1. I have all this stuff over here. -2, -3, -4. I'm just going to put negative pi on there. Negative pi, right? It's just a number. They're all just numbers. Okay, real numbers. Okay. So then what is this set 1 to 5? What is this infinite set? That's saying that we are here at 1 and we go all the way to here 5. But as you can see, what I'm trying to emphasize here is that there's infinitely many numbers between 1 and 5. We're not just talking about the nice whole numbers. Does anybody know what those are called? 1, 2, 3, 4, 5? Integers, right? We're not just talking about the integers. We're talking about all real numbers in between there. So you have 1.2, 1.7, 1.34, 5, 6, you got whatever you want. And that's the point of like pi, 3.14, it goes on forever, right? Pi never repeats itself. So every decimal in between 1 and 5, that's what we're talking about here. Every number in between, every real number, okay? So those are real numbers. And so that's where, again, you could say things like pi is an element of 1 to 5, right? 7 is not an element of 1 to 5. Okay. Does that make sense? Any questions there? Okay, so that's called interval notation, where we write it kind of like well, we call this an interval. So we can write the same thing in set notation. I think that'll help as well. So that set notation brings our brace back. But with the braces, I was writing everything out. Can I write out all the numbers from 1 to 5? No, right? It would take me forever. I could have 1, 1.01, 1.001, 1.001. I could never get anywhere, right? I'd be writing forever. So we use some variables. We can say, okay, this is actually the set of values x such that 1 is less than x and x is less than 5. So we start to introduce variables, some sort of placeholder, because there's infinitely many, we can't write them all out. So you'd read this as the set, and you say of values or of x values, so let's say x values. And you don't have to use x. We can use whatever letter you like. We can put a in there. You want to put anything you want. X is very common. A is very common. And then this is just a vertical bar, and it's meant to be kind of taller than, well, this is a number 1. Sorry, my 1 and my vertical bar look the same, but that's just a vertical bar, and you read that as such that. Again, you see the whole math is a language thing, but I don't have to write all these words. Just writing this to someone that knows their math and knows how to read this, can read this as the set of x values such that x is in between, and then you get conditions. So these are conditions on x. Okay. We write this sort of stuff all the time. I'm teaching Calc, bless you. I'm teaching Calc 3 after this, and we're going to write sets as representing x, y's, and z's because you start thinking about 3 dimensions, and you have to put restrictions on all 3 directions, like how far can you go, what you can do, and it all comes down to just this. It all comes back to those fundamentals. So for this class, we need to see these things. We need to be able to read them, need to understand them. Basically, like I said, math is a language. We're trying to understand the language. And then we also need to understand the basic tools of this math language, which are functions and those sort of things. Which all of it's just notation. It's all just notation. It's all just a language. Like I said, I talk about, trig. It's you put the letter COS, so those letters mean something. They mean the cosine function. The cosine function means something. It means a sine wave, a sinusoidal wave, and stuff like that. So that's where we're going. All right. So notice very importantly here, or let me ask this question: is let's say 5 an element of? So I'm going to put a question above it because I'm not saying that it is. So is 5 an element of the set 1 to 5? Okay. What do we think? So it's not. Okay, and so it's kind of a trick question, but it's just notation. So how do we say if it is or if it isn't? How do we know if we want to include that last point or not? So I want to include 4.9, right? I want to include 4.99. I want to include 4.9999999. So I can't choose the largest value that I want to include. Do we see? So I have to stop somewhere, but I want to stop there somewhere, and I want to say whether it's included or not. So notice, and the way you could have answered that question is that what I'm showing you here is that this parenthesis corresponds to this inequality. And how do we read this? X is strictly less than 5. What does that mean? Can x be equal to 5? No. If I want to equal to 5, how would that look? I put the little bar underneath, right? Be less than or equal to, right? So that's how you could have known how to answer my question. So really that parenthesis corresponds directly to that strict inequality. It's called the strict inequality if it doesn't have the equal bar. Okay, it means strictly not equal, right? Strict inequality. Okay, so then how do I say what if I do want to include 5? What if I want 5 to be part of my set? I need a different notation. Anybody know or want to guess, since I already showed other mathematical objects here? What are we going to use to show that we do want to include the 5? Oh yeah, greater or less than or equal to. That would be on the right side. That'd be the set notation. What about the interval notation?
Bracket.
A bracket, exactly. So then that's where the square brackets come in. So then we have, so the answer here is no. So let me do this. It's not equal to, so no. I'll just put no. I'll just put not an element, but I'll just put no. And so we can write the exact same set, or I'm sorry, not the exact same set, almost the exact same set. Oops, sorry, my phone's not silent. Okay, almost the exact same set. And now 5 is an element of, is an element of 1 to 5. And I can write this as the set of x values such that 1 is less than or equal to x, which is less than or equal to 5. Okay. That makes sense? Do we see the difference? So if we call these things something, like we call this set A, we call this set B, you don't have to write that, I'm going to erase it in a second. You could say that B is exactly 2 elements bigger than A, right? But they're both infinite, which is kind of weird. And there are different sizes of infinity, which is weird to think about, right? Infinity is this concept that really nobody really understands. We use it. We have math and notation to represent it and show it and try to mathematically manipulate it. But we can't really grasp the concept because we can't represent it, right? We can't do it. Nothing's infinite. But technically, those are both infinite sets. You could say they're size infinity, but B is 2 elements bigger. So whatever the infinity of A is, B is 2 bigger. There, we do have mathematical notations for that as well. We call things countably infinite, which basically means that you can correlate the elements of a set to the counting numbers, like 1, 2, 3, 4, 5. But we're not going to get into that. That's beyond this class. Or not. Well, it's not even that it's harder. It's just different than this class. It'd be a different direction. We could easily go from this discussion to that discussion, but it would be a totally different direction. Okay, so that bracket is the, or maybe I'll, no, yeah, you could. Okay. Is that clear? Any questions there? Yeah.
Why did you highlight the bracket and the greater?
I'm just trying to help you understand the significance of the bracket. I'm just showing you that that's what that means. Do you want me to highlight the other one too? So this is, well, let me use a different color. It's just because I didn't do it yesterday, but I'm going to make these notes available to you. So if you look back at these later, I want you to understand what it is that we're talking about. Like, why did I write these things down? So the fact that this is a parenthesis is why this is a strict inequality. I'm saying these two things represent the exact same set. You understand?
Yeah.
So we have interval notation, we have set notation. They represent the exact same thing. And so I just want to make sure you understand the parenthesis indicates the strict inequality, the non-inclusive. Does that make sense? Yeah. That's just an instructing tool on that. And yes. Any other questions? Okay. So you can probably guess what we want to do from here. That's, as you can see, a lot harder to talk about than what we talked about up here. It's like, oh yeah, okay, 1, 2, 3, 4, 5. I can see those. The students in the class, I can see those. Even the population of the Earth, right, is not infinite, but it's almost infinite because it keeps changing. There's births like every few seconds, right? And there's deaths every few. So it would be a hard thing to map and to write down or represent mathematically, but it's still not infinite, right? The Earth is finite. So then we start to talk about the operators. So what is that? Why do I have that there? That's the same thing we just talked about. I think this is directly from Alex. I think I was either showing this or someone last term asked about this from their Alex. So this is, you're going to see these sort of things in Alex. C is the set of y values such that y is less than 3. That's maybe we should represent these on the number line. Yeah, let me put this on the number line. I don't think I can copy that one. So how is this number line different? You don't need to put the number 0. All you need is the number 1. But I'm going to put the number 0. Over here, we'll put our negative pi just for fun. We'll put our number 1. We don't need to put all those numbers in between. We just put the 5. And so how do we show that we want to include it? Is that we, with the brackets, we use the closed point. So here you notice I did an open circle. That was very intentional. That means you do not include that actual endpoint. And then you have a closed point here. And then we're talking about all the numbers in between. So now you have 3 ways of representing the exact same set. This, and this all say the same thing. Is that clear? So we have interval notation, set notation, and then a visual, like a graph, graph plotting. Okay? And I think what Alex should ask you to do all of those, unless you already knew this stuff and already did it on the initial knowledge check, in which case it might not ask you to, but in general it will. It's part of your homework. Okay, so I guess, I've been talking a lot. Let me give you a second. Represent these 2 sets for me, C and D. I don't remember exactly why I chose those. Either someone asked about it or I just chose something off of Alex last term. But let's represent those in interval notation and visually. It probably just says graph. I'll just put visual, it doesn't matter. So that's all graphs are, right? Graphs are just visual representations of some sort of data, some sort of information that we want to convey, right? I said everything about math is a language. The more you understand that, the more you think about that. If you look at something like, why are we learning this? What is this? Like, what is all this complicated notation? It's the way it goes. And as you get higher in your math, the notation just gets more complicated because we need more ways of representing stuff. It's like, well, squiggly braces already chosen, square brackets already used. Let's create some new symbol. Let's use something else. Or like the alphabet, of course. Math has basically claimed the alphabet, right? We use every letter A through Z, and then that's not enough, so we start to use the Greek letters. We use alpha, beta, gamma, and so on. It's just the way it is. Like I'm sure you all know, angles are usually represented with a theta, right? That's not a normal alphabet letter. But alpha, beta, gamma, those are often used for angles as well. We'll use those this term for sure. But they're just used to represent something, to placeholder. Okay, so this is a little tricky, so let's do this first one, C, and then I'll give you like 10 more seconds to do D in case you're stuck, because I didn't actually show this yet. What I showed are still contained intervals. You could say this is called a closed interval when both the endpoints are included. This is still called an open interval because, like I said, what is the largest number in this set? We don't know. We can't say it. You tell me it's 4.9, I'm going to say it's 4.99, right? You say it's 4.999, I'm going to say it's 4.99999, right? There is no largest value. So this is an open interval. There is no biggest value. Does that make sense? But what is the largest value in this set? 5, right? That's it. There's no debating it. There's nothing bigger than 5. There's 4.99999s or whatever, but that's it. 5.1, 5.01, those aren't in there. 5 is the biggest set. So this is called a closed set. Maybe I should write that down as well. So this one is closed. This one is open. Where did I write it originally? Up here. Okay. So the ones I have down here are open, not just because of the strict inequality, though, because this one has an inclusive inequality, and that's what those are called also. Maybe I should write that down. This is strict inequality, just so you know the words I'm saying. This is called an inclusive. Hopefully you see how those words, again, these are just English language words. Hopefully you can see how they make sense. If you want to include the number or not, it's inclusive. If you don't want to include it, then it's strictly not equal, right? Strict inequality. Okay, so what does that look like in interval notation? Anybody care to tell me? So what is the right endpoint of the interval, like this? What's going to be my rightmost value that I'm going to write down? 3. Am I going to have a bracket or a parenthesis? Parenthesis. And that's why I highlighted, right? Why do we have a parenthesis? We have this parenthesis because of this strict inequality, right? Okay, now what's my left endpoint? How small can I go? Infinite, as far as I want. So this direction as far as we want. So how do we represent that? Hence, what? No, sorry. How do we represent that? Infinity. Hence the infinity, like I said, we don't really understand, doesn't really mean anything, except we kind of get it. We're like, okay, we want to go that way forever. So we have a way of representing that way forever. So, well, yeah, for you guys, that, yeah, left, right? So we say that this is negative infinity to 3, right? That's what that means. So that is all values, and the x or y, or it doesn't matter what letter you're using. So I used a y here. So this is the set of values y less than 3. That's what that is. And so I'm going to erase this in a second, but just if you've all thought about like plotting points, if you've done the coordinate plane before, x is the left and right direction. So you'd say x to positive infinity, that would be this direction. And then this one would be y to positive infinity. Okay. But that's just, again, arbitrary. It doesn't have to be x and y. It could be s and t or r and l. It could be anything you want. So if don't get too caught up with those letters. You know, x is usually the horizontal movement, and y is usually the vertical movement. But that's just because we do it so often, people use the same notation. Okay, it's not like set in stone. Okay, so then visually, what does this look like? So again, I'm going to put the number 0. You don't have to put the number 0, and if you don't even want to, you don't have to. I just want you to make sure you understand. 0, of course, gives us the sort of division. The number line has 2 parts, the right, positive, the left, negative. When you introduce the second number line, as I just showed you, we have 4 parts, right? 1, 2, 3, 4. So when you have, so that's 0, or the origin there, the 0, 0, gives us sort of that division. But anyway, so we'd have the number 3 over here somewhere. And then we want to go this away forever. You can draw like an arrow or something if you want to. I don't really care. I'm just, as long as you understand what's going on. I mean, some people put like an arrow. I don't care about that. And especially when using these pens, it gets kind of messy. Hard to do. It's a little easier with pencil. And then we have to decide on 3. How do I indicate to my reader, how do you indicate to me whether 3 is included or not? You use an open circle. And so we say an open circle to say that it's not included. That's, and usually we're pretty dramatic about it. It's not really anything. We just put it there so you know. Right? It's, again, all of it's a language, all a way of communicating. So now anybody that knows this stuff already can read this, and this, and understand exactly what values you are talking about in whatever setting you're talking about them, right? You might be talking about the domain. You might be talking about the solution of an equation or an inequality. You might be talking about the values that you use to test, like the parameters that you tested within. Not infinity, of course. You can't test within infinity, but it could be anything, just representing data. Any questions there? Okay, so like I said, I'm literally going to count to 10. I'll give you like 10 more seconds to do part D in case you were stuck on part A, or C, I'm sorry, set C. I'll now do set D. It's going to be very similar now. And this is also usually the way I do class. I like to do some stuff, show some stuff, talk some things out, have you do some things. That was part of my expectations, right? You'll attempt everything. You don't have to get everything right. I'm not going to come around and check if you did it or check if you got it right or anything, but you should try. And it's actually, you learn more if you got it wrong, but you shouldn't erase it if you got it wrong. Just kind of cross it off, say, I thought it was this is what it's supposed to be, and kind of make sense of it to yourself. That's also the point of that journal, that reflection. It's like, hopefully you kind of internalize all this stuff. That's what we're trying to do. And I said I was going to count to 10, and I forgot because I started talking. So I do that, though, but I forgot. Or I did. I was distracted. All right, so what is this going to look at interval notation? What is, or where is the 9 going to be? Is that going to be my left endpoint or my right endpoint? Left endpoint. Okay, good. And then is it included or not included? Included. So I'd use a bracket or parenthesis? Bracket. Okay. Any questions there? We all see where all that's coming from? We get all that? Okay. And then I have a little comma, which just says it's 9 to something. But again, as soon as you put this or this, it's infinite. So even if I put 9.1, right, there is an infinite, don't write this down because it's not what we're doing. But even this is an infinite, not 9 to 9. That's not an infinite set. Even that's an infinite set, right? There's 9.01, 9.001, 9.0001, all sorts of numbers in between 9 and 9.1. Okay, that's 9 and 1/10. So in other words, there's numbers smaller than 1/10, right? There's tons, infinitely many. So as soon as you put a bracket or parenthesis, you have to understand it's infinite because it's a comma. And that was, again, my point of this up here. We just put this comma, but how do I know that it's finite? Well, because I use the braces, right? That's a huge difference, huge difference. But we always use commas, or you always use those ways of separating them. Okay. All right, so you just have to make sure you can read all this stuff. All right, and then, of course, what is my right element going to be? Infinite. So I'm going to put positive infinity. Notice this one's negative, that one's positive, and I put a parenthesis. I'm sure this must have been a student question. I must have done, because I probably did all this stuff with them, and then they had this in their homework, and they didn't see the connection. Okay, but hopefully you all see it. All right, and then again, maybe now I won't put 0 this time because you don't need 0. And you don't even put it, like it doesn't have to match this one, but because I have it right up there, I'm going to put 9 like over here somewhere. Okay, there's my 9. And then I want to go everything to the right. And then how do I show that 9's included? A close point, exactly. Now I will say technically, like outside of like pre-calc or outside of this class, we're trying to be very, very specific. You might just not put anything because then it's sort of like, okay, it's there. Putting an open circle says it's not included, right? That's very clear. It's very dramatic. So if you don't put that, it's like, okay, it's there. But for this class, very much 100%, I'm going to want to see a very dramatic closed circle, so I can tell that it's that you know what it is I'm trying to test you on. Okay. All right. So that's basically sets. That's what we need from sets. And now we have to do unions and intersections of infinite sets, which gets a little trickier, but this should help us. Questions? Feeling okay? Too fast? Too slow? Good? All right. All right. So now let me actually see what I do have in the notes. We'll talk about those in a second. Those are our infinite or our famous sets. Right. So let's just look at these questions here. Oh. So this box, you notice I'm not going through all the notes in detail because that would take too long, but you have access to all these and you could have these in front of you, or you do have them in front of you. So what is this? This is just all of the possible ways of writing an infinite set. That's all of them. So when we want something more involved than that, you have to combine to the infinite set. So like a union of sets. So this is an open, A to B, but notice with the brackets, and then this is half open, half closed. So you'd actually say half closed, half open. And this is half open, half closed, right, reading from left to right. But notice what that means. That just means the left endpoint A is included, the right endpoint B is not included. I don't know, you probably can't see my cursor. I know it's really small. I've tried a million things to change that. This little dot, it's really hard for me to follow too, this little pixel. I can make it bigger, and it'll be this gigantic arrow like you can on all computers, but as soon as you put it over here, it goes right back to the little pixel. It's the size of like 1 pixel. It's crazy. But that's a one-note flaw, I guess. And then this is negative infinity to infinity. That's all real numbers. So that's the entire number line. And then this is a bold R that we use to represent the real numbers. Okay, so that's a bold R, and this is the way I usually write that. Okay, so it's just an R, and it's meant to be bold R, and it represents all real numbers. Okay, any questions on this table? I didn't do any of these graphs. Let me do just one interesting one like this one. So this would be A here, B here. What am I doing? Close point here, open point here, everything in between. But notice A and B can be anything you want, right? It could be, pi to 17. It could be, -3 to 0. It could be whatever you want. Just A to B. That's what those are showing. What? No, sorry. No, I make mistakes. Please ask. No. Is that okay? Any questions on this table? I don't want to fill it all out unless somebody wants me to. Any of this unclear? Any of the left-hand side, any of this stuff? Again, it's just the same thing we were just doing, just a whole table of it. Okay, so now, like I said, well, what if our set is more than just A to B, right? What if we need more than just one interval? It's just one in each one of those nodes is just one interval, but that's every possible combination. Also, actually, something that we should notice. And let me ask you, what do we notice about the infinities? Anything jump out at you about the way about that? I'm telling you, this is every possible interval location you're ever going to use.
Infinity is in parentheses.
Infinity is never included. Does that immediately make sense to us or not? Is infinity a number? No, it's a concept. Like I said, we don't really know what infinity is. It's just okay, that way forever. You don't actually get there. Like, what is infinity? There's no such thing. So you should never put a bracket around infinity. I've taught this class 100 times, and I always have students that do it. It happens. I'm going to mark it off, cross it wrong, whatever. But notice what I'm showing you. This is every possible interval that you're ever going to write, at least in this class. I will tell you, you get to there some weird things way beyond, like maybe PhD things, or even maybe just master's level stuff where they say, okay, let's include infinity as an element, but that's getting weird stuff. That's getting to weird stuff. So you might actually see a bracket in infinity in a true mathematical thing, but your chances are you're not going to read those for at least 6 years, okay, 7 years. So you won't see anything like that. So in all of undergrad, all of this class, never put a bracket on infinity. Never, ever, ever. Okay. Is that clear? Okay. All right. So let's talk about these three. This we actually just talked about. So this is just wrong. So we just talked about that. So never bracket. Whoops. On. And I'm going to put plus or minus because, of course, it's either one, either infinity. Doesn't matter. You never put a bracket on an infinity. Okay, what about this one? What about this interval? What's weird about that one? It's in the wrong order. And that might seem like, it's like, okay, it really kind of means the same thing, right? If I go from 3 to 52, 52 to 3, it seems like it should be the same set. But that's where infinity really becomes tricky. You'll learn something in Calc 2 where we'll look at infinite sums. And it turns out you're literally just adding an infinite number of elements, right? But the order in which you add them actually changes the sum, actually changes the value. So infinity is a really weird thing, and so the order matters. So I'm just starting in pre-calc right away. We say that this is not allowed. We always write smallest to largest. Always. Okay? Always, always. And so again, when you're drawing a number line, you're like, okay, here's 3, here's 52. It's like, okay, this really seems like it'd be the same either way. And it really would be if you're just talking about the sets. But we don't go that way. It doesn't work that way. It gets confusing later. All right, let's answer this question. The way I might write this in class, I'd probably put 0. I put element of. I put a question mark above it so you know that I'm not saying that it is, because otherwise it would just look like I'm saying that's an element of that. And then I put that. Okay. So is 0 an element of that infinite set? What do we think? Yes, right? And now I'd say more important than yes. I mean, yes is true, so let's get rid of that. We'll say yes. In other words, so now you do read this. 0 is an element of there. How do you know? So it's infinite, right? We can't list it all out. 0 is not shown there. What makes it absolutely 100% clear to you that 0 is an element of that set? Okay, you're right, but okay. No, you're right. That was a poorly phrased question. I'm trying to kind of foreshadow to a more general mathematical concept here. That's very important. Forget the fact that it's like 3 and 6. Like, say you don't even know where those numbers are or whatever. It doesn't matter. What about those numbers tells you that 0 is in between? Yeah. It changes signs. Exactly. The change in signs, and that goes back to what I was saying up here. So we're over there somewhere with the number line. 0 is the division point between the positives and negatives. And so that might sound obvious, hopefully it does, but this is actually a mathematical theorem. It's very important. It's called the intermediate value theorem. When you get back to your graphing, it basically says that your values, if they're up here and then they're down here, they must have gone through 0, right? To change from positive to negative, you must go through 0. And so that concept is very fundamental. So that's what I think is the more interesting part here. we know for sure that 0 is in that set because we have a negative and we have a positive. And there's no way to change signs and not go through 0. Does that make sense? That's the kind of the bigger picture. Here, I mean, you answered the question. It's in between -3 and 6. That's completely true. But I'm just trying to get to a bigger thing there. All right. So now the true problem here, the true question here. Well, this is like a quiz question for sure. This sort of thing. So I give you 2 infinite sets. You have to know how to read them. You have to know how to represent them. You have to know how to union them or intersect them. So let's actually do both. Well, it doesn't matter. Let's just do, well, let me just give you a second to think about it. See if you can tell me. So you see the set S is 2 to 5. The set T is 4 to 7. So and you can say exclusive and inclusive. This is the 2 to 5 exclusive. This is 4 to 7 inclusive. If you want to read it like a math teacher, okay, or a math person. But you can also just see it. It's there. And what I'm asking you to do is tell me what is S intersect T, which is exactly the same as this infinite set intersected with this infinite set. So hopefully you see this is the same thing we did with the finite sets, but the finite sets are a little easier. So I was using those to introduce the notation. And remember, intersection is what's common to both of them. It has to be, so I'd be the intersection of the 2 pre-calc classes. Bless you. Anybody care to venture their thoughts? It's okay if you don't want to. Yeah.
You want me to just say what I think it is?
Yeah. What do you think it is? Yep.
Parentheses 2, 5, 7 bracket.
No. It's not quite. It's all right. I appreciate it. Yeah.
Line with 4 and 5 on it, and then the 4 is closed and the 5 is
The
open.
4 is closed, the 5 is open. Yes. Okay. All right. So this is, and you drew a line, which is what I'm going to do in a second. So if you're wondering how we're going to figure this out, you don't have to just look at it, and it is hard. So don't feel bad if you got this wrong or if you don't see it. So it should be a bracket on 4, a parenthesis on 5. Okay. So that's it. Now, how do we see that? How does what is, obviously you can just look at it like I am and like we did, but the easier way is to visualize it. So let's think about what is S, right? 2 to 5. So here's 2, open. Here's 5, open. We want everything in between. So before I even move on, any questions on that? We see that. Okay. So what is T? T is 4 to 7. So since we're trying to compare these, let's put 2 here. Let's put 4 where it should be. Let's put the 5. And let's put the 7. Well, what is this one actually? This is close point at 4, close point at 7, and we want everything in between. Any questions on that? So right now the 2 and 5 are just extra, but that's for us to be able to visualize and see what's going on. So with the intersection, so that's what we want here. Now an S intersect T, we can visualize that as well. So that is a new set. It's just a set of values. So it's a set of values that's in both though. So notice these values aren't there, right? The 2 to 4, in 2 to 4, that's not in the set T, so it's not going to be in the intersection. These values, 5 to 7, they're in T, but they're not in S, so they're not going to be in the intersection. So we want what's in both. So we can see that it's from here to here and here to here, right? And then you say, okay, well, so you can see 4 is included in both sets, so that's the bracket, but 5 is not in this set, so it's not in the intersection. But we have to still stop at 5, right? Because 4.9999999999999 is in there. Oops. Okay, so we can see that here we want 4, we want 5, we want a bracket, we want a parenthesis, and everything in between. So that's essentially like the work you can show. Because again, it's infinite, right? You can't list it all out. There's really no other way to compare them visually. But that's a nice thing with that visual. And of course, you can also just see this and know what it is as you practice and get used to these sort of things. Like I don't expect that from anybody now. That's what I asked you to do. But that was the challenge part to it. And if you couldn't do it, like I said, don't feel bad about it at all. Okay. All right. And make sure you understand this, though, right? As long as you understand it, that's this point. Any questions? Like I said, it's important to write down your own thoughts first. because then that's how we learn. We learn more from our mistakes than what we get right. Right? If you take a quiz, you get all things right. I still remember something I got wrong when I took a pre-calc class. And I'm not even making that up. I'm dead serious. I won't say what it is because it's a terrible mistake that nobody should make. But it haunts me, right? I'm serious. Like these things, you get like a 97%. And you're like, what the heck? And that 3, that whatever took you that took that 3% away, you remember those things. It's the way our brains are wired, which is really not nice. It's also why we remember like sad and traumatic events more vividly than we do happy things, right? It's all these happy times, and we don't. It's terrible. It's the way our brains are wired. But anyway, that's not math class either. Any questions on this intersection? Okay, so let's do the union too, just because we might as well. There's really no reason not to. And you already have the visual. And make sure just to make sure 100% we understand what the union is. And then we'll move on from there. We still have 10 minutes. Okay, good. Yeah, right? Yeah. Now remember, union is like addition. You're taking both and just mushing them together. So if we took, this class and the other class and put them all together, you all be in there, I'd be in there, all the other students would be in there. It'd just be everybody. Okay? But the elements do have to be in one of the sets. So let's start with what should be the easier part. What is the largest value in the union? 7. And that's included, so it's going to be a bracket. What's the smallest number in the set? Okay, good, right? So we can't say it. We can't actually say the smallest number, because again, that goes with the whole 999 thing, but it's going to be approaching 2. So the smallest number, so actually what we call this a lower bound. It's not the smallest number. It's not in the set. It is a lower bound for the numbers in that set. But you don't have to know that either, so it's okay. That's the lower bound for all the elements in that set. So you can't go lower than 2, but everything bigger than it is included, right? Up to 7, of course. Okay, good. Any questions? Why this is a parenthesis? Why this is a bracket? Any questions on the union? Do we see it? Usually the visual helps. The main thing is just notice that 2 is not included because 2 is not in either set. Right? Remember that's a parenthesis, so it's not included in either one. Okay, but everything bigger than 2 is in this one, so we have to have that included. Okay, good. All right, so that takes us to famous infinite sets. I already asked for one, and we got the response of integers, but these are names that you just have to recognize. Integers is one of them, so we're going to make them a little more formal. Where are those? Down here. Okay. So actually, let me not even. I'll write what because you have to write it. So let's do this. All right. So we have the integers. All right. So let's see. This is. I think the most okay. Let's go back. Sorry, we're not going to do integers first. So these are called, let's start with the natural numbers. And sometimes these are called the counting numbers. So when you're counting objects, like the chairs in this class, what number do you start with? 1, right? And then do you count the 1.5 chair? No, the next thing is going to be 2. And the next thing is going to be 3. The next thing is going to be 4. But then where do you stop? Right? You can't stop. It goes on forever. So it's an infinite set. It's called the natural numbers. Some people call it the counting numbers. You don't have to know this, but I think they're neat. So usually students think they're neat as well. There are letters that represent each one of these sets as well. The naturals are represented by a bold N. You don't have to know that, but you probably, has anyone not seen the bold R? I mentioned the bold R for all real numbers. Usually that's something that's shown in like a lot of math classes because we use it so often. Or you get solutions that are all real numbers, or you get domains that are all real numbers, and so we wanted to put that bold R. So you don't have to know the bold N. It's just kind of neat. Okay, and it's on my cup if that matters to anybody. It's not, but anyway. All right, so then we technically have the whole numbers. This one's not as important, but it's just different. So the whole numbers, I guess I'm putting the colon over here, okay, are exactly the natural numbers except they include the number 0. I actually don't even know if there must be a number. Is it maybe a bold W? Did I put that over here? I didn't put them over here. I think it's a bold W, but We're not going to do anything with it, so I'm not going to write it down. The natural numbers are important. But the most important, really, what I really want from you, which is why I wrote it first, are the integers. Okay, but now that we have those, it'll be easier to describe what the integers are. Okay. So really, the integers are what we're going to use. That's going to be the smallest sort of set that we deal with. And then we're going to call the natural number something else and the whole number something else in a second. So you'll see. So you don't really have to know those names. The integers are then positive and negative whole numbers, basically. So you have the ... -3, -2, -1, 0, 1, 2, 3, comma, ... Okay, so you see no decimals, right? No fractions. So, but they're not just positive numbers, they're not just counting numbers, so we call them whole numbers, right? All those. And that's represented with a bold Z, if you're interested. And that one's, you don't have to know that if you don't want to. All right, so now what I want to say is instead of, and I know my alarm just went off for the 5 minutes, so this will be a fine spot to stop. Let's talk about the positive integers, the negative integers, so hopefully you see what I mean. We're basically going to consider like the integers as like our smallest set, like that's the one we're going to deal with, the base set, and then we're going to categorize it differently from there. So we're going to have non-negative, and positive integers, or sorry, non-positive integers. As you move forward in most classes and most settings, I think people tend to just refer to the integers. So it's positive integers, negative integers, non-positive, non-negative. That's what we're talking about. So there'd all still be the integers of the bold Z. So these don't have their own symbols for these in particular cases, but I just want to talk about what does that mean. So what does the word positive mean to us? What?
We have the number, I guess. You can't have negative or something.
Right, not negative or, like what does positive actually mean? Greater than 0. Greater than or equal to 0 or greater than 0? Greater than, right? Strictly greater than. Does that make sense? Not the equal to. 0 doesn't have a sign. 0 is a special number. Like I said, the whole division between positive and negative. 0 is no sign. Not positive, not negative. It's neither one. Okay, so the word positive means strictly greater than 0. So I'm going to write that here. Strictly greater than 0. That's a terrible. So if we talk about the positive integers, then we must be actually talking about the counting numbers, the natural numbers. Same thing. Those are your positive integers. So what are your negative integers? Everything less than 0, right? So that's your -3, -2, -1. But -1 is the largest. Remember, negatives are funny. -1 is the largest negative integer. Okay. So then what do you think I mean by non-negative? So, right, that includes 0. So non-negative, so it's not allowed to be negative, but also including 0. So this one means greater than or equal to. I guess I should put that this is less than. I think the blue and the green kind of look the same, but it's okay. Those could be, it's fine. So then non-negative means 0, 1, 2, 3. And you'll see immediately why we have these words, why we use them. They show up in definitions as ways of describing these infinite sets that we want to talk about. I think non-positive is probably a little more rare, but still makes sense. Okay, so you can see why we don't need the counting numbers or the whole numbers. Instead of calling them counting numbers, we're going to call them positive integers. Instead of referring to the whole numbers, we're going to say non-negatives, right? So it's the same set. So we just refer to the integers, and we have the positive integers, non-negative integers, and the negative integers. Like I said, non-positive, I don't think there's a setting in this class where we'll talk about non-positive, but so these three are very, very, very commonly used. Okay, but you see they're just referring to sets of values. All right, and that's a good place to stop. Any questions there? So these are just names you have to know. So in class, like in a week from now, I'm going to say the integers. And so a set has to come to your mind. You all have to think about the same set when I say the integers, because that's what I'll be thinking about. If I refer to the positive integers, you all have to be thinking about the same set. And that's the whole language thing. We have to be communicating the same. And I will keep using that language. Whether you're keeping up with it or not is up to you. Okay? And never be afraid to ask. Always ask. If you say, well, can you remind me what the integers are? And I'll write this thing down again. Okay? All right. All right. There's more to this, but we'll do that tomorrow. That's fine. All right.